So for the next pair of examples, they make use of an approach to systems called system dynamics, which is not the totality of how you can deal with systems. I hope I've been getting that point across. But is a really, I think it's probably the most widely used mathematically based approach to systems. It got started back in the 1950s. Jay Forrester at MIT got this going, and then some of his students wound up taking it even further in ways that I'll describe in a moment. One of his students was Donella Meadows, who I was fortunate enough to have as a friend for many years. And I highly recommend this book, Thinking in Systems by Donella Meadows, which I think is probably the best introduction to system dynamics and broader system thinking for systems that have feedback loops in them. Is really the, and systems that have feedback loops in them are where a lot of people who describe themselves as being into systems, it's the ones with feedback loops that they really like, because those get to be pretty interesting. She was one of the co-authors, and indeed the main, I think of her as the main author for this Limits to Growth 30-year update. And for all, she was one of the Limits to Growth original authors. And if you aren't familiar with the Limits to Growth, I also highly recommend this as a way to see how system dynamic work got applied and in effect gave birth to the sustainability movement. So I highly recommend both of these books to go deeper into what we're about to go into. So with system dynamics, there wind up being some very specific pieces that you use in a system diagram. The first piece is called a stock. And a stock is something where you put stuff. So you think of it as a reservoir. Examples of stocks are everything from your bathtub to actually any of the containers in your fridge, to a bank account. It doesn't have to be material stuff, it just has to be stuff you can count, stuff you can add in and in some way keep track of how much is in that stock or how little, and how does the level in the stock go up and down. So just think of it as a container where stuff can go up and down. And the way it gets to go up and down is through flows. So stocks and flows. And the flows carry stuff in and out of stocks. However, those two aren't enough. You also need some kind of place where you can do some additional calculations, and these are called variables. And then to tie it all together, they have what they call links. So these four things wind up being the basic elements for system dynamic diagrams. And let's look at a particular example. I put this together this past week on a wonderful site. Here we are on insightmaker.com. So I told you about kumu.io. Insightmaker.com provides free, and it really is free, open source, system dynamic modeling software where you can build models. You can make them either private or public. This one is public, and I will provide a URL for where you can go and play with it. So what's going on here is that I've got three sort of input parameters, if you will. The initial birth rate, or the base birth rate, the base death rate, and the available food, and I'm winding up measuring food in terms of the number of it's not necessarily people, but the number of animals or people or whoever is making up this population could be supported. And since this is a simple model, we just have 100 over here. So think of it as rabbits. Okay? And the population here in this stock will grow based on the number of births, and it will decline based on the number of deaths. So this flow arrow comes in, meaning it's adding to the stock, and this arrow goes out. And buried in here, let's see if I can do this. If I come here to population, as soon as I move my cursor over it, there's this little equal sign that pops up. If I click on that, I go into the equation editor for this particular thing, and you'll see there's a number 2. Well, that's the initial value of the population. I figured I couldn't start with 1. If we were going to have any births, we had to have at least 2. The base birth rate is just a number, but it's not just a number, because over here there's a slider, and I can actually change that base birth rate by moving the slider around. I'm not sure whether, because this is my model, for when you go and look at it from a public point of view, I know you can move the sliders around. You may not be able to get in to monkey with the equations, but I want to show you how they work. Here, off with births. Now this gets a little more complicated, but it's really not bad. This says that the base birth rate times this thing which is 1 minus the population over the available food. So as the population grows, the birth rate's going to go down, on the theory that as there's more population, you get as there's more stress on being able to get enough food, is the idea that's being communicated. And then all that times the population. And this times the population being fed by something that depends on the population, is exponential growth. This is like your interest in a bank account. And this little link here that goes from population back to births shows that there's a link carrying the size of the population into the calculation for how many births are going to be. Deaths has a similar equation, except that here it's a plus sign. So as the population grows, the idea is that there's more stresses in the system, and so the death rate goes up. Okay, let's look at what happens if we just let this model run over time. So here we are over a span of 20 years, starting with our population of 2, it eventually grows up to a population of about 80. During that time, the birth rate grows for a while, and then it declines. All that while, the death rate is growing, and by the time the birth rate and the death rate are almost the same, then that means that the stock won't change, because there are as many being added as being taken away, and so the stock stays at the same level. Suppose we were to make the available food 50 instead of 100, and let's run the simulation again. Now, it looks just the same. All that's happened really here is a change of scale. Remember, we were about 80 last time, and now we're about 40? And this is often what happens in systems. If you change some of the numbers, the pattern doesn't change. It's like rubber, but the pattern that's built in to this structure is going to give us very similar results. And now I want to point out, for those of you who either were around or saw the first What Time Is It videos, one of the things in that was this S-curve with reproduction limited domain and resource limited domain. that look like that? Basically, we've just created a model that generates an S-curve based on the notion that down here, you're into sort of exponential growth because it's easy to have a lot of births. Up here, you get the other side of the S-curve because the deaths are rising and the births are decreasing. Now let's look at another example. Home heating. Here we have different kinds of weather, and inside a house, we have a heater and a thermostat. So we're going to make a model of this. The stock in the center of this is the indoor air. And for those who want to be fussy about the physics, it's actually the heat of the air, which is why we have a link out to a variable called inside temperature. We have a heater as the inflow that provides more heat into the indoor air. And then we have a heat flow that can actually go in both directions between the indoor air and the outside air. And whether or not, which direction it flows in depends on the insulation and the outside temperature. And that whether or not the heater comes on depends on a thermostat that looks at the desired temperature, where you set the thermostat, and whatever the inside temperature is. So there are equations in each of these. I won't go through them all, but I do want to, though, just look briefly at this thing. So if we look at outside temperature, what you're going to see is this isn't an equation. This is a graph. So within Insight Maker, you have the opportunity to put in data in a way that doesn't need to be on the basis of an equation. It can just be whatever. You can paste it in, or at least import it in various different forms. And you'll notice here that I generated some really wild weather. If you look carefully here, temperature goes almost up to 100, and then 2 days later, it's down at 10. Now, some places in Missouri might actually get that. But I'm, of course, doing this for illustrative purposes. So let's run the simulation. Cancel down here. Whoa! So this is a wild ride. The heater is supposed to be keeping the inside, the heater and the thermostat are supposed to be keeping the inside of the house at a constant, more or less constant temperature. They're doing that along here. It fluctuates up and down a little bit, but that's the way heaters work. Here, when it's hotter than the desired temperature, the heater is off. This is a measure of whether the thermostat's on or not down here. The heater's off, but it doesn't stop the heat flowing into the house. And here, the heater just isn't strong enough. And so it can't keep the house warm enough, and the heat goes down. Undersized. So that's with, what does this say over here, 4.5? This is the insulation thickness. Now suppose we bump that insulation up to 6 and run the simulation again. This time, there was enough insulation so that the heater was well sized for this particular temperature. But there was still nothing that could be done by the fact that the house would get warm, because heaters don't cool off houses. So these are relatively simple models. You can build much more extensive models, but those more extensive models are almost always built out of chunks of this sort. And really, when you get down into it, each one of those chunks can be understood in a pretty straightforward way. See if there's anything. I do want to note that this here, going from inside air to inside temperature to the thermostat to the heater is a loop. And it's a loop that is designed to, it's what's called a balancing loop as opposed to a reinforcing loop. It's a loop that is designed to keep things in a steady state regardless of what's happening in the context. So there are an awful lot of systems. These complex adaptive systems like human beings and societies and other things of that sort have a lot of homeostasis systems, systems that are designed so that the system stays pretty constant while the context fluctuates. Okay, let's go back here. And you remember that graph. There's some things I want to point out about this graph. First of all, there are time lags between when the outside air reached its peak and when the inside air reached its peak, and when the outside air reached its lowest point and the inside air reached its lowest point. Time lags are very common in systems that have any kind of stock in them, because what happens is that you start the flow, but it takes a while for that flow to fill into the stock. And then whatever it is that the stock is then influencing gets you again. And it's like the way flows are kind of like pipes. Have you ever turned on the hot water in a bathroom somewhere in a house and it comes out cold? And sometimes gets even colder and then eventually gets hot? Well, that's because you send the signal by turning on the faucet, but there's a whole long pipe between you and the hot water heater that may very well have gotten quite cold. So that's another time lag piece that and I point that out because of the way in which time lags show up all the time in our daily lives, and yet they confuse us because we expect you do something and it happens. The result happens. You do something and the result happens. And systems help us to understand what the time lags are. I talked about the way in which there was this section that was too hot, and then another section that was, this is Goldilocks here, right? This is just right, and this is too cold. Well, I think of each of these as tipping points, and each of these sections, if you think back to the what time is it presentation where I, at the very beginning, talked about system domains. So each one of these is a system domain. The behavior of the system in this section is that the heater and the thermostat are irrelevant, but the amount of insulation does have an effect. In this section, the heater and the thermostat are doing their job, and the insulation, it's all working. In this area, the heater is still relevant, but the thermostat has become irrelevant, and it's not able. So they're distinctly different behavior patterns for the system in these three sections. So now I'd like to talk a little bit more about tipping points. Watch. So what's going on here? It's very common when you have some sort of tipping point like that, where the scale tipped, that what's feeding it is some kind of continuous input. You could have a sharp input leading to another tipping point, but it's kind of like then that sharp input is a tipping point in some ways. But instead, you can have continuous change that, because of the structure of the system, will give you a shift, a tipping point type shift. And I want to illustrate that in a political context. Here's the Gallup poll asking people in the US, do you think marriage between same-sex couples should or should not be recognized by the law as valid with the same rights as traditional marriage? This is the should not be, and this is the should be. And you'll notice this is 1996 here up to 2014. You'll notice that there's a very gradual increase in the should be and the corresponding gradual decrease in the should not be. And somewhere right around 2011, 2012, it gets to a place where there's a crossover. Now down here are the number of US state law changes in the various different years. So there was one in 2008, one in 2009, etc. And then you get over here about where the crossover happens, and you get 2 and 5 and 18. Now, maybe this is just a coincidence, but maybe it isn't. The gradual change in public opinion then leads to, in effect, a tipping point in terms of what happens. This isn't only court cases, this is also referenda and things of that sort. And because the structure of our system is majority rule, then the place where a certain opinion becomes a majority sometimes winds up creating a tipping point. There are lots of places where it doesn't, but sometimes it does. So I've got another illustration, which I'm going to have to describe, of a tipping point. This is a tarp over a recycling container. And I'm not going to tell you the whole story behind this, but toward the end of a rainstorm, I realized that there was this wonderful metaphor unfolding on this tarp. And so I got out with a camera and I took a little video of it. It's not very high production value. And to help you see what's happening here, I have put in some little red circles to sort of draw your attention to various places. But overall, what's happening is rain is falling on this tarp, and because the water beads on the tarp, initially the rain that falls forms into little beads and just kind of hangs there on the tarp. Every now and then, one of those drops of water gets big enough that it reaches its tipping point and starts rolling down the tarp. But here we're not talking about just one tipping point. We're talking about literally hundreds of tipping points. So this gets much closer to what goes on in society. As I play this, I'm going to warn you that initially you're going to say, "My, this is boring. Nothing much is happening. Yeah, an occasional one goes down, but why is he showing us this? It's very much like real life." Something does eventually happen. So let me play it. Ah. So that's an example of how you change society. Societies are big, complex, adaptive systems with lots of homeostasis that resist change. But when change happens in a lot of different places, little bits of change here, a little bit of change here, a little bit of change here, as it keeps moving in a kind of organic fabric, eventually you get to places where you can get these bigger rushes. Those bigger rushes are prepared by many, many small shifts.